following is an introduction to rubberized asphalt concrete, commonly referred to as RAC. What is RAC? Asphalt rubber is a blend of asphalt cement, ground-up tire rubber, and other additives. The definition of asphalt rubber has been identified by several ASTM standards. Rubber modification of asphalt concrete mixes can be accomplished using two distinct wet processes: the high-viscosity agitation method and the low-viscosity no-agitation method, commonly referred to as terminal blend. The wet process requires thoroughly mixing chrome rubber modifier, known as CRM, into hot asphalt cement. The resulting blend must be held at an elevated temperature for a designated period of time to permit an interaction between the CRM and the asphalt cement. The high-viscosity agitated wet process uses the largest amount of rubber tires and is most effective in gap-graded and open-mix designs. It is not suitable for dense graded mixes. It is also most effective when used on relatively thin surface lifts. Gap-graded mixes are used as a structural layer equivalent to conventional dense graded hot mix asphalt. Open-graded mixes are used in surface friction courses. RAC has increased resistance to rutting, fatigue, and reflective cracking. This is a function of the RAC binder content and modification. Production methods for the high-viscosity asphalt rubber binders are essentially the same for both hot mix and spray applications. The primary difference is the importance of coordination of asphalt rubber and hot mix production to assure that enough asphalt rubber binder is available to provide the desired hot asphalt cement mix production rate. Operations are split into two components: aggregate production and binder production. Aggregate production follows the normal manufacturing process for conventional hot mix asphalt. This is comprised of the quarry mined or quarried aggregate being processed into the specified gradations as identified by the mix design. This is commonly referred to as the aggregate skeleton. Additional equipment is required on-site to produce the RAC asphalt rubber binder product. The binder production process begins with the delivery of asphalt binder. The standard grades required by Caltrans for RAC are PG 64-16 and PG 58-22, although other grades may be used depending on the prevailing climate. PG-graded asphalts have replaced the aged residue or AR designation. The heat tank is required to raise the asphalt cement to a range of 400 to 425 degrees Fahrenheit. The blending unit is where chrome rubber is blended with the elevated hot PG binder. The chrome rubber arrives on-site in 2,000-pound super sacks. The sacks are emptied into a waygate hopper. The PG binder is simultaneously metered into the blending unit. The proportions of the RAC binder components are metered by a control panel based upon the binder design. Once thoroughly blended, these materials are then pumped into the reaction vessel. The blended mix typically contains 18 to 22% chrome rubber, with particle sizes ranging from number 8 to number 10 top size, and can include extender oils and other additives, such as anti-strip agents. The reaction vessel is a tank that contains motor-driven agitators that keep the rubber particles dispersed in the hot asphalt. This allows the RAC to interact for a designated period, typically 45 to 60 minutes, with continuous mechanical agitation. The CRM particles swell and exchange oils with the asphalt cement. The RAC binder and aggregate are now combined using conventional HMA processes. The RAC mix produced is now stored in silos, ready for delivery to the job site in trucks. Temperature of the material at this point should range from 320 to 335 degrees Fahrenheit. Temperature management is essential to successful RAC mix placement and compaction. It should be noted that high-viscosity RAC mixes are very sticky, have a rubber odor, and are not conducive to large amounts of handwork. Materials must leave the plant at a minimum of 315 degrees Fahrenheit. tarping of truckloads is generally specified. RAC may not be the best choice on projects with the following conditions: long haul time or distance, site temperatures less than 55 degrees Fahrenheit, or if rain is imminent. Good practices for conventional HMA placement shall be adopted. Special attention should be paid to temperature management. Coordination of the binder production, mix production, mix delivery, placement of material, and compaction are essential to provide for the service design life of the pavement. In short, density is controlled by the material temperature and compacted effort. 95% of the compaction density can be achieved during the breakdown rolling process. A steel drum breakdown roller must be used in vibratory mode with a mat temperature above 280 degrees Fahrenheit. It should be stressed that rubber tire rollers shall not be used whatsoever for RAC compactive efforts. The paver should be equipped with a fully operational screed leveling device. RAC mixes and laydown temperatures should be monitored using infrared and stab thermometers. These devices should be calibrated on a regular basis. RAC should not be placed with an ambient or road surface temperature of less than 55 degrees Fahrenheit. Traffic should not be allowed on the finished mat until the surface temperature of the mat is below 150 degrees Fahrenheit. If this is not possible, a sand or dust blotting application should be applied at an application rate of 2 pounds per square yard. This acts as a bond breaker and not a cooling agent, and shall be applied only after all compaction effort is completed. Some agencies have used lime marinated water, but prevailing stormwater regulation must be considered. Approach to structural design depends on the intended purpose for the RAC pavement, which may include preservation, maintenance, rehabilitation, or new construction. It should be noted that Caltrans Highway Design Manual allows the use of a thickness equivalency factor of not more than 1:2 to RAC gap-graded mixes when compared to conventional asphalt for reflective crack retardation only. Asphalt rubber provides the following engineering benefits: improved durability as a surface layer, resistance to fatigue cracking, resistance to reflection cracking, resistance to aging, reduced thickness design, and lower life cycle costs. Asphalt rubber provides the following environmental benefits: diversion from landfills, reduced tire stockpiles, recyclable product, and noise abatement.